Today we are going to look at 4.5 binomial sampling, distribution, and applications. What do we mean by binomial sampling? In binomial sampling assumes selection from a two-category population with numbers in one category labeled. So if we have, for example, pie chart, we are gonna label if this part is called P, which is successes. And we know that obviously this part is not the success part. And with the binomial sampling, there is a fixed number of selections, and there's a fixed number of selections, n, or sometimes n is called trial. And with each selection, independent and each having the same probability p, a success will be chosen. What do we mean by independent is whether or not we achieve a success on the selection in no way affects the probability of achieving success on any other selection. So here we have an example. From many thousands of users of a new experimental drug designed to cure specific form of bladder inflammation, it was found that 60% were cured. So suppose we randomly select n is equal to 15 individuals from this large two-category population. What percentage of the time would we find 12 or more cured? So as you can see, it's a two-category population, and we can, if we want to make a pie chart, we can say that more than 50%, which is about 60% here, is P is equal to 60% cured. So what's left over here, 1 minus P equal to 40% not cured. And we have given that n is equal to 15 individuals. And we have a large population. So a large population is defined as any population at least 20 times the size of the sample. So what are we gonna do with this question? First thing we need to do is we need to find mu. What is our mu? Mu is equal to, as you remember from the last chapter, n times p. In our case, n is equal to 15. P is equal to 60%, which means 0.6. So therefore, we have 0.6. When we multiply these two, we get 9. This is our mu. What about the standard deviation? Standard deviation can be calculated actually with n times p times 1 minus p, and then we take the square root. Our n is again the same thing, 15. P is 0.6. 1 minus p, which we already calculated, which we already talked about here, which is 40%, which means 0.4. When we do this calculation, we get something like 1.897. And if you want to approximate this, it's going to be 1.9. Next thing we need to do is, we know our mu is equal to 9, and sigma is equal to 1.9, standard deviation. Now, if we want to do our normal curve, how we are gonna put these values on our normal curve? We know that, let's do like this. We have n is equal to 15. So we go up till 15. And our 9 is the mean. And when we are doing the normal curve, we do the histogram. And this histogram borders are important. So over here, it's gonna start from 8.5, goes until 9.5. So R9 is our mu. And what we are looking in the question is, we are looking at the what percentage of the time would we find 12 or more cured. So if my 12 is somewhere here, right? If you look at the histogram over here, which is gonna consist of this part is 11.5 till 12.5. So therefore, when we are calculating 12 or more cured, we are gonna start our data values from 11.5. What do I mean by this is, let me do another one over here. When we are doing our calculation, we have to consider our mean is equal to 9 over here, and we are looking for 11.5 or more. Okay, over here, this area we are interested in. How are we gonna find that area? As we already know previously, z can be calculated using x minus mu divided by sigma. I know my x, which means the data value, is 11.5. Mu is 9. Divided by sigma is equal to 1.9. When you put these numbers on your calculator, you will get 2.5 divided by 1.9. So therefore, we get z equal to 1.32. And what we're gonna do with this z-score, we need to go back to our z-score table. And as everybody knows by now, z-score is giving the area between 0 till, now it is z-score over here is 13.2. Sorry, I made a mistake. I meant, let me put this here, 1.32, right? When you look at the z-score, which is z is equal to 1.32 on the z-score table, on our table, which is gonna give the area between 0 and 1.32. So when I looked at it, I got the area z-score 1.32 is equal to 40.66%. This is this part. So as you know, on a normal curve, we have symmetric, and the left side is 50% of the area, right side is the 50% of the area. If the whole thing on the right side is 50%, what is left for this part, question mark part? It is gonna be 50 minus 40.66% is gonna be equal to 9.34%. So this is telling us 9.34% of the time we will achieve 12 or more cured when we randomly sample 15 from our population, and which is very not likely. Let's look at another example. Out of millions of assembly line batteries produced last month by a large manufacturer, 6% were known to be defective. Out of 170 randomly selected batteries from this population, find the probability that 14 or fewer of these will be defective. So if you want to visualize, again, let's look at our population and the percentage. We know that we have 6% known to be defective, something like this small percentage over here. P is equal to 6%. How can we write this in terms of decimal? 0.06. If that is 0.06, what is left non-defective is 1 minus P is going to be equal to 1 minus 0.06, which is 0.94. So we found our p-value and 1 minus p-values. What is next? Next, we need to look at our mean. Mean is calculated by n times p, which is equal to 170 times 0.06. By the way, this is a binomial sampling. Why is that? Because of we have 170 fixed selection, and each independent and each having the same 6% probability that a defective battery will be chosen. So when we do, let's go back to our calculation. When we do this calculation, we get mu is equal to 10.2. So we got our mean 10.2. Next thing we need to do is standard deviation. Standard deviation is equal to n times p times 1 minus p, and then take the square root. So this is going to be equal to 170 times 0.06 times 0.94. When you do this calculation, you will see you will get 3.096, which is sigma is equal to approximately 3.1 when you round it to 1 decimal place. So I have these values, mu and sigma, for enough for my calculation. Next thing we need to look at is our normal curve. So let's look at it. If we have a normal curve, we know that our mean is 10.2. And when we do the histograms, again, we are looking for 14 or less, but we want to cover all parts of this histogram. Therefore, we have to consider this border 14.5. So this is 13.5, that's 14.5. Since we are looking at less than 14, we have to start from 14.5 and go down. So we are looking for this area. So I know that the x value which I am looking for is 14.5, and I need to find the z-score for this part. How are we gonna find the z-score for this part? So I know that x is equal to Z is equal to X minus mu over sigma. So I know my X. X is equal to 14.5. Mu was 10.2. And sigma was 3.1. So when you do this calculation, you get 4.3 divided by 3.1, which is equal to 1.39. So we got our z-score value, which is 1.39. So therefore, z is equal to 1.39 at this point. What am I going to do with this 1.39? I have to go back to my z-score table. When you look at on the z-score table, as you all remember, we have the values 1.3 and 0.09, where these two intersects over here somewhere, the value which we are looking for. And that value is gonna give us the area between the mean till 1.39, this area. Okay, but as you can see, we are interested in this area 0 to 1.39 plus the whole left side. So when you look at on your z-score table, you see that z is equal to 1.39 is equal to 41.77%. But we are looking for 14 and less, therefore this part is 41. Actually, I can go back. This is, oops, let me go back. Okay, this is 41%, 41.77%. This part is 41.77%. And we know that the half of the normal curve is also 50%. And since we are looking for this whole area, all we need to do is we have to add up 50 plus 50% plus 41.77%, which is equal to 91.77%, which is answering our question. We can say that 91.77% of the time we will achieve 14 or fewer defective batteries when we randomly sample 170 from our population.